We're going to start out today with a little thing I call a quizkin. It's not a test. It's not even a quiz. It's just an ungraded little opportunity for you to review and just check if you really understood the stuff that was in the last podcast. So today we're starting out with this one about methyl salicylate. Another name for methyl salicylate is oil of wintergreen, made up of hydrogen, oxygen, and carbon. I want you to stop the video when you see these quizkins and try to work out the solution. As soon as you start the video back up, I will have the answers sketched in here, and if you got the right answer, I'll show you where to go to start the video and skip the solution. If you didn't get the right answer, you want to probably just keep watching the video, and then I'll work it out and give you a complete solution. Ready? Go. Well, here's the empirical formula that you end up with if you got this right. It's C8H8O3. For the second answer, the molar mass turns out to be the same as the molar mass of the empirical formula, so the molecular formula is also C8H8O3. Well, this is an indirect analysis, and here's the solution. I start out with my 12.24 grams of CO2, and I want to find out how many moles of carbon I get from that. So I'll do a little dimensional analysis here. I know that carbon dioxide is 44.009 grams per mole. I also know that every 1 mole of CO2 is going to give me 1 mole of carbon, and when I work this out to 4 significant figures, I get 0.2781 moles of carbon. So that's going to be important. I'm also going to need ultimately to know how many grams of carbon to do this indirect analysis. So I'm going to continue this calculation here, and I'll multiply by the molar mass of carbon, 12.011 grams per mole. This tells me that there were 3.341 grams of carbon in the original compound. I'll do a similar thing for water. There were 2.522 grams of water, and I want moles of hydrogen out of this. Water is 18.015 grams per mole, and for every 1 mole of water, there are 2 moles of hydrogen. So this gives me 0.2800 moles of hydrogen. And if you're looking carefully here, you can see that there's probably going to be a 1-to-1 ratio carbon to hydrogen. Again, I want to know grams for analysis later on, so I'll multiply by hydrogen's molar mass, which is 1.008 grams per mole. And this gives me 0.2822 grams of hydrogen. So here's what this means. If I take the total mass, which is given to me, of 5.287 grams, and subtract the 3.341 grams that was carbon and the 0.2822 grams that were hydrogen, I will end up with 1.664 grams of oxygen. I really don't want grams of oxygen. I want moles of oxygen so I can do my mole ratio. So I'll divide by the molar mass of oxygen, which is 15.999 grams per mole. And this will give me 0.1040 moles of oxygen. So here are my 3 mole quantities, 0.2781, 0.2800, and 0.1040. Obviously, oxygen is the smallest one, so I'm going to start out by making a ratio of carbon to oxygen in this compound. 0.2781 moles of carbon divided by 0.1040 moles of oxygen. This comes out to 2.674, and I really can't round that to a whole number. It's not close enough. It's not even close enough to 2.5. You have to be within a few hundredths of a fraction to round to it. This is pretty close to 2 2/3. Sometimes it's easier to put these as improper fractions, so this is an 8/3, I'm going to call it. So 8/3 moles of carbon for every mole of oxygen. I'll do the same thing for hydrogen. 0.2800 moles of hydrogen were in the compound compared with 0.1040 moles of oxygen. And this gives me 2.692, a ratio of hydrogen to oxygen moles. And again, that's not close enough to round to anything except for the fraction 8/3. So that would give us a formula, C8/3, H8/3, O1. But we can't have fractional subscripts, and so we'll triple everything. Multiply all the subscripts by 3. So that gives us C8, H8, O3. Now, to find the molecular formula, we want to find the molar mass of our empirical formula first, C8H8O3. And if I take 8 carbon molar masses, add 8 hydrogen molar masses, add 3 oxygen molar masses, here's what I come up with, 122.149. Now, the problem tells us that 122.15 is the actual molar mass. The actual molar mass matches the molar mass of the empirical formula, so C8H8O3 is not only the empirical formula, in this case it's also the molecular formula. Well, today we're going to talk about chemical equations. We've been doing a lot of stuff with formulas, and now we're going to move into the area of chemical change and the reactions that actually occur. Chemical equations are shorthand, quantitative representations of real chemical reactions. So how are we going to tell what's going on in a real reaction with shorthand as a sort of a model? Well, one thing we have to do is we have to put symbols in there and formulae. So symbols like AU, for example, for gold, and formula like H2O for water. Those are going to be part of the equation. And then the other thing that we're going to do is we're going to use something called coefficients like 2 or 3 that are placed in front of the symbols of formula for chemical species to balance them, to show how they actually occur in nature. Because we know that matter isn't created or destroyed, and atoms can't be altered from one kind of atom to another in ordinary chemistry. And so we're going to have to find how nature really does this by bringing them into balance and making that law hold in our model so it matches reality where it always holds. So how do you write balanced chemical equations? Well, here are a few absolutes. These are things that you have to do. One is you have to write the unbalanced equation. It's not really an equation until you balance it, but the formula representation correctly. So that means if you're writing an ionic compounds formula, it's got to be right. If you're writing a molecular formula, you got to look at those prefixes and make sure you get that right. The other thing is you adjust only the coefficients to bring the equation into balance. Never change subscripts. That's not something that you can touch. Once the formulas are correctly written, the only thing that you can do is balance with coefficients. It takes a lot of experience to efficiently get these right, but here are some tricks that can help you get started. One trick is look for species that are easy to follow across the arrow. Like in this example that's here, oxygen is in every compound in here, hydrogen is in 3 of the 4 compounds, but sodium would be an easy one to balance because sodium only appears in one reactant on either side of the arrow. So I would first off start balancing this by balancing my sodium. Here's another trick. Polyatomic ions that don't react, that don't come flying apart as part of the reaction, you can balance them as a unit. So like in this reaction, I have phosphate here and I have phosphate here. I can keep phosphate together and balance it as one unit rather than having to balance the phosphorus and the oxygen separately. Another thing that's sometimes helpful is remembering that water could be modeled as HOH, and sometimes it's easier to spot H's from acids and OH's from bases by doing that. Like in this reaction, if I write water not as H2O but as HOH, well, I can put a 3 here to balance the H's that I find in my acid, and then that tells me I have 3 OH's, and then I'll know to balance with a 3 here. Another thing is you should let the subscripts guide your selection of coefficients. Think about least common multiples. Like here's an example. I have O2 here, that's 2 oxygen atoms, and I have O3 here, which is 3 oxygen atoms. The least common multiple of 3 and 2 is 6, and so I want to have 6 O's on both sides. A 2 here would do it, and a 3 here would also give me 6 oxygens. And then I just finish out the balancing by making sure aluminum's all right. That shows up a lot. Here's another one. When the only source of an element is a diatomic molecule, using fractional coefficients can sometimes help you. This is temporary. You can't really have fractional coefficients in most cases, but it's a way to get the problem solved. Let's take a look at this example. If I'm balancing this equation, I'm going to balance carbon first because carbon's only in one species on both sides by putting an 8 here. Then hydrogen is the same situation. Hydrogen's only here and only here, so I'll balance that next. If I put in 9 in front of water, that balances it. Now I'll go back and work on my O's. I have 8 times 2, that's 16 O's, plus another 9 is going to give me 25 O's. Well, if I look back at my source of oxygen on the left-hand side, it's O2. That means no matter what coefficient I put in front of O2, it's going to be an even number when I multiply that number times 2. And 25 is odd. So here's what I can do. Temporarily, I can say 25 halves of an O2 would balance the equation. How do I get rid of that? Well, I just double everything. So the 1 in front of C8H18 becomes a 2. 25 halves times 2 is just 25. 8 times 2 is 16. 9 times 2 is 18, and now the equation is balanced. The point of balancing equations is that they provide us with stoichiometric equivalencies, or what we often call mole ratios, for doing stoichiometric comparisons. Like in this example, this is a balanced version of an equation that we've seen before today. I'll pick out 2 of them at random, 3 moles NaOH for every 1 mole of H3PO4. And that's based on the coefficients. 3 in front of NaOH in the equation, and a 1 in front of H3PO4, which is not written, but it's implied. Here's another one. 3 moles NaOH to 3 moles of water. Or we could reduce that to 1 to 1. And again, that comes from the coefficients in the balanced equation. Why is that useful? Well, these mole ratios, or stoichiometric equivalencies, can become factors in the dimensional analysis technique that's very helpful for solving problems, like this one. The question is, how many moles of sulfuric acid, that's H2SO4, react with 0.366 moles of NaOH? And here's the balanced chemical equation. Well, here's how we can use stoichiometric equivalencies in dimensional analysis to solve this problem. I'll first start out by writing down what I know, 0.366 moles of NaOH. What do I want this to turn into ultimately? Well, I want to know how many moles of H2SO4 are going to react with that. Here's how I can convert. To cancel moles of NaOH, I'll put 2 moles NaOH on the bottom from the stoichiometric equivalency that I get from the balanced chemical equation. That's the coefficient in front of NaOH. I want H2SO4 in my answer, so I'll put the equivalent number of moles of H2SO4 on top. And since there's no coefficient in front of H2SO4, that means that's a 1. When moles of NaOH cancel, the only unit I have left is moles of H2SO4. My answer is 0.183 moles of H2SO4. When mass starts to get involved in these equations, we start to have a little bit more difficulty because those mole ratios are, well, mole ratios. So the 3 and the 2 and the 5 coefficients that you see in different equations, those only refer to moles, not mass. They aren't gram ratios. Gram ratios would be entirely different. So here's what we have to do. We have to convert mass into moles. But we know how to do that. It involves molar mass. Here's an example problem. Here's a reaction. It's given to us and it's balanced. The question is, what mass, so there's mass, of Fe2O3, that's this thing, is needed to produce 86 grams of iron, which is a product. Stoichiometric equivalencies are involved, but so will molar mass be. I start out with what I know, 86.0 grams of iron. What's my target? Where am I going? I want to know how many grams of Fe2O3 are needed. Well, molar mass of iron is 55.847 grams per mole, and I put the grams on the bottom so they cancel. Now I have moles of iron. Once I have moles, then I can use a mole ratio. So I put moles of iron on the bottom, and I want Fe2O3 to be my answer, so I'll put moles of Fe2O3 in the top. My ratio is 1 Fe2O3 for every 2 moles of iron. Moles of iron are now gone. I'm dealing with moles of Fe2O3. My target is not moles, but grams of Fe2O3, so I'll multiply by Fe2O3's molar mass. And that turns out to be 159.691 grams per mole. Now I've converted to grams of Fe2O3, and the only thing left to do is my arithmetic, which gives me this answer, 123 grams of Fe2O3.